Yo, 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 future so bright. I wear these special shades. Now, today was the eclipse. We had that this morning. So, yeah, I don't think this will be particularly useful nowadays. But anyways, we're at chapter 4. We're going to look at section A. We're going to look at the development of atomic models from a historical perspective. So for Christians in science, we're not so interested in finding the ultimate truth. We are trying to find workable models. And the reason why we're not so much interested in finding the ultimate truth is science, that's not the purpose of it, to find the ultimate answers for life. Science, we can observe and measure things and try to explain how some things work, but it's not going to give us life's ultimate meaning. You know what? God provides that ultimate meaning, our origin, our purpose, and our destiny. Just something to think about. So we look at 500 BC, looking at the Greeks here. We got this dude named Democritus. We have the Spartans, okay? And basically the Greeks sat around, talked, and they said matter is made up of separate, distinct, which means we can tell what it is, particles. It could not be divided infinitely without losing its properties. So if we kept cutting it, cut, eventually it's not going to be that anymore. It's going to be something different. And that's where we get the word atomos. The Greeks came up with the word atomos, which today we get our word the atom. Okay, bunch of history happened. Not going to worry about that now. 1782, French dude named Lavoisier showed that mass does not change in a chemical reaction. The law of conservation of matter, he proved it. He also discovered that air was a mixture of gases. This guy also wrote the first modern textbook for chemistry. He was the father of modern chemistry. French dude, 1789, lost his head in the French Revolution. 1799, Proust. He showed that water by mass is 89% oxygen and 11% hydrogen. Did these two know each other? Don't know. Could tell you though, Ben Franklin was schooled by this guy. Ben Franklin would go and listen to him talk. Moving on. So 500 BC through the Renaissance, about 1700, our big question is matter made up of particles, or is it just some continuous thing and that's it? We actually did get our answer. In 1800s, we found something called the law of definite composition. Definite meaning we know this to be true. Composition, what is something made up of? Every compound is formed of elements combined in specific ratios by mass that are unique for that compound. So salt, NaCl, is one atom of sodium, one atom of chlorine together. That's it. That's what table salt is made. There's nothing else. Let's look at water. 2 hydrogens, 1 oxygen. When they combine, they form water. There is no other composition of water. It is H2O. It doesn't matter where you are. 1803, we got Dalton. Now, he came up with the first experimental model about atoms. He had some theories. Combinations of atoms from different elements form compounds. That's pretty reasonable. We got hydrogen and oxygen, hook up, and you got a water. Atoms of different elements have different masses. So an atom of gold isn't going to weigh the same as an atom of hydrogen. No, it won't. Now what else did he do? He assigned relative masses to atoms of various elements. He wasn't particularly successful with that. Moving on, 1800, we had an Italian dude named Alessandro Volta, Italian physicist and chemist. He discovered methane gas, CH4, and this is a gas that we produce. Think flatulence, think fart gas. That's a lot of it is methane. Now he also invented the electrical battery as well. Copper, zinc, salt water, soaked paper, combined those together to form the first batteries. They were known as pila, P-I-L-A. Okay, and that's like the first battery there, just to give people an idea. Moving on, 1897, J.J. Thompson. He experimented with cathode rays. That's him up there with his cathode ray tube. And the cathode ray, think of the old school computer monitors. Think of the televisions that your grandparents had, the big boxy ones. So he discovered something. He discovered there were negative charged particles out there, and they're called electrons. Now, electrons have very little mass. They don't weigh much. And his explanation of the atom was the plum pudding model. Think of pudding, what you eat, and inside this plum pudding, there were the raisins, which were, in his idea, the electrons were scattered throughout the entire atom. That's what he was thinking. 1909, now Rutherford, he discovered the nucleus. That's in there, New Zealander. He used alpha particles, or helium atoms are alpha particles. The mass is about 7,300 times greater than the mass of an electron. So we're talking about something that's pretty heavy, pretty huge. Now it also has a +2 electrical charge. Electrons have a -1 for every electron out there. And then there was the Geiger experiment. Here's the deal. Geiger was a student working for him. Geiger and another guy went to Rutherford and said, we want to do this experiment. Rutherford said, yeah, go do it, don't bother me. I got more important things to do. They took a piece of gold foil, made it really, really flat, and then they put a film around it. And then they had this box that had this beam that had all these radioactive particles, this alpha particles, they're helium atoms, and they would release it to go through into the gold foil, and they were expecting all of it to go, as Jim Morrison would say, break on through to the other side, and it turned out, no, that's not true, because it was bouncing. Now I show that on the FET thing, okay? You'll get to see it later, unless you're reviewing. Here's the thing, something's up. Something is seriously up. It should be going through to the other side. It's not. There's something bouncing. So what did we learn from the experiment? The nucleus, very small compared to the entire atom. The nucleus also has a positive charge. Positive particles in the nucleus are called protons. The number of protons in the nucleus is called an atom's atomic number, Z. So that was kind of a huge thing. We thought that atoms maybe were fairly solid. They're not. They're mostly empty space. The little tiny thing is the nucleus. But we got to move on. 1932, we found another piece of the puzzle. James Chadwick finds the neutron. But he noticed something. How did he get there? Well, we know how much protons weigh, we know how much electrons weigh, so when we were analyzing on the atoms, we found, hey, something was off. Something was off, and that's, it wasn't adding up. Something's missing. Something's there and we're not seeing it. And that's when he observed there were neutral particles in a sample of metal. In other words, particles that did not have a plus or a negative charge. And that's where the neutrons come in. They are a little bit heavier than protons. They are. So we found out, J.J. Thompson found the electrons, Chadwick found the neutrons. Okay? But we have to talk about electrons. And that's where 1913, Bohr. We know that electrons existed to begin with. We know how much they weigh. But how do electrons move around in the atom? Because Thompson was saying, hey, they're just scattered inside the atom, yada, yada, yada. Rutherford found, hey, the atom is mostly empty space. So what's going on? Well, if electrons are negative and the protons are positive, why aren't they connecting? They're not connecting. That's the point. So what's going on? Are they moving? How are the electrons arranged? And that's when we get into something called spectroscopy. Okay? Now, Bohr thought a couple of things. One, electrons needed to move, and they had to have energy in order to keep themselves from crashing into the nucleus. There was something about that. Had to be. Okay? So, now we got to go back. What is spectroscopy? We can analyze light emitted or given off by matter. So we can analyze the light that's in your ceiling, you know, in the room that maybe you're watching. We can analyze the light from a candle. We can analyze that. And we can analyze the light that's absorbed by something as well. That's another thing. The simplest spectroscopy we have is the rainbow. Wait a minute, what's a rainbow for? The sun gives off sunlight, rain comes down, and what happens is sunlight goes through this water and it breaks up into the different parts of the light. And that's a fairly important idea. Okay? So, what is this rainbow? What are we talking about? It's a spectrum. It shows the different wavelengths of light and energy. The spectrum is like the fingerprint of light. That's the thing. It's like a fingerprint of light. So we have fingerprints here. That's the fingerprint of light. And this is more spectroscopy. We're all familiar with this, that is continuous, but this is an emission spectrum where we see lines being given off. Here it's the opposite. The lines are absorbed. Okay? That's a little bit different. So what did we learn? We learned that Bohr was right. There are energy levels there. And it worked great for the hydrogen atom. But the moment it went with the helium atom, then things did not work out. So Bohr was correct. There are basic energy levels, but there's so much more. Okay, these levels are quantized. In other words, quantized means energy is given off in specific amounts. This mean here tells you a very important idea. Electrons gain energy, they jump levels. When they drop levels, they lose the energy, and that's where we get the light. Yeah, can you imagine? Now, what else did we learn? Well, electrons can do one of three things. They can absorb energy, they can give off energy, and they can be in the ground state. So absorbing energy, they can jump to a higher energy level in doing that. Well, wait a minute, where is this energy coming from? It's an outside source, primarily the sun. Primarily the sun. If the sun wasn't there, then we would not have the energy. We would not survive without the sun, period. It's huge. So they absorb energy, they give off energy when they go down the energy levels, and then there's the ground state, which is the lowest energy level in the system. In other words, Monday morning for your typical high school student. Ding! Okay. So with that here, this is just showing you a diagram of how the energy goes absorbed and what the color of light would look like when it goes down. The more levels it goes down, the higher the level of energy is given off. Okay? Now, 1935, modern physics. De Broglie said light acts as a wave and a particle. You have photons that are packets of energy. Electrons have a dual nature, wave and a particle. I do need to move on here. Heisenberg, with his uncertainty principle, that's a pretty big thing here, because what he was saying, and he showed it mathematically, we cannot predict where electrons are going to be and how much energy they have. Thence, we talk about the idea of orbitals. Bohr talked about levels, but in each level you have orbitals in there. And those are probable positions of electrons. We're not certain. And he got a Nobel Prize in 1932 in physics because of this discovery. And it led to the creation of the electron cloud model. This is it right here, where the center is the nucleus. That's the solid part of the atom. The rest of it is empty space, and you got electrons that are just bouncing all over the place depending on how much energy they have or don't have. And that's really the big history of the atom, going from the earliest time we can talk about the Greeks. We worked our way through the Renaissance. We talked about the French dudes like Lavoisier and Proust. And then we looked at Thompson, we looked at Rutherford, we looked at Bohr, and then we looked at Chadwick, then we looked at de Broglie, and then we ended up with Heisenberg. What's my name? Hey, that's it for the first part of Chapter 4, the history. How did we get to our part of the atom today?